Yeah, so some of the things I'm going to talk about today are pretty technical. I'm going to try and give the nicest possible introduction to whatever is the key idea, and I'm also going to give the two different applications or results that motivated it. So the first theorem is going to be a statement about moments of L functions, and this, I guess, is maybe due to maybe you have to write 6 names and some of them repeated here. So it's Blomer, Fouvry, Kowalski, Michel, Milesevec, plus Kowalski, Michel, Sawin. So let me write this down and let me explain what it means. So we're going to take F cusp form, which can be holomorphic. It can be holomorphic or Moss of level 1. And yeah, which I guess I only know one example, so we can take it to be the delta function. And that's pretty good. And we take P to be a prime. Then if we sum over Dirichlet characters mod P, the special value of the L function at the central point squared, this is given by the obvious formula. If you're very, very clever and this is obvious to you, it's L sim2 f1 over zeta of 2 log p plus beta f plus O of p to the minus 1 over 145. Or rather, the what's the point? This error term?
Yeah.
I mean, the theorem would be false if there were no error term.
Yes, I'm complaining that nobody can see.
Oh, I'm sorry. Well, let me. Some people maybe can. Anyways, it's a. Let me maybe write it larger. It's a power-saving error term, and the power is 1 over 145.
Okay.
Oh, you may be. And the constant here is depending only on f.
What's beta f?
It's another constant that depends only on f, and you can get it. So you can get it by some kind of residue calculation, but it's supposed to be. So this is a linear. It's a linear function log p, and the coefficients have something to do with L functions, and these are both certainly. Well, I mean, the error term is much smaller. And so this tells you to a pretty good amount what the second moment is. And there's a related natural question to ask, which is if I have two modular forms, what's the correlation between these special values? And so, yeah, I can write. If I let F and G be two level 1 cusp forms, then the same sum, L of F tensor chi 1/2, L of G tensor chi 1/2 conjugate is, again, what some people may find the obvious main term, although not really to me, L F tensor G1 over zeta of 2 plus the same error term.
The first one, the power saving is the new thing, right?
Yeah.
No, the first
Yeah.
one, so you could get a positive proportion and not zero and things like that.
Yes, and so we are, there's many conclusions of that form you can get, and there's a paper in the works by the union of these two sets, which will hopefully state all the most important results of that form. But yeah, so this was proven except for one step of the argument by these 5 people, and then these 3 people, which have some overlap, did the remaining step of the argument. And
The point, I think the answer is maybe the error term is not so interesting to anybody, but that allows you to put a modifier in.
yes, exactly. So if you put, meaning just putting chi of some rational number, if we put this in the sum, then we can also get a good estimate here. No, the second one is not log p. So somehow this really should be L of f tensor f at 1, but it has a pole. And so the pole means that there's a dependence on log p. And so there's a more general version that tells you the right thing, and it's always a polynomial in log p. And the degree is always, I think, an order of a pole.
This kind of fits into some sort of L functions, moments, conjectures.
Yes, so there are conjectures for what these should be, and the conjectures agree exactly with what we said, except the error term and the conjecture is much better. But we got some cancellation in the error term, but we haven't. Yeah, this is pretty conjecturally well understood, I think. So if you don't like L functions, or I have a second application, which is theorem 2, where we will again take f a cusp form of level 1. And we define p a prime and a any real number. And recall the definition of Dirichlet convolution. So the Dirichlet convolution of the Fourier coefficients of f and 1 is just defined to be the sum d dividing m lambda f of d. So this is also the Fourier coefficients of an Eisenstein series on GL3, if you enjoy Eisenstein series on GL3. And the result we have about this function is a level of distribution result. And I will write it down, and I'll explain why the interest in this result comes from. So it's going to cover what happens when you sum this on, I guess I need to have one more parameter, a invertible residue class mod p. If we sum this function over an arithmetic progression of everything congruent to a modulo p, this is equal to the main term you expect, which is just the average over all arithmetic progressions that are not multiples of p. So we're going to sum over n less than x, and p is 1, plus a, here we don't do a power saving error term, we just do an arbitrary power of log. So this constant had better depend on the power of log, and this is whenever p is greater than x, so the 1/2 plus 1 over, and I wrote down what the power is, and I forgot it. Well, I wrote bigger than a half. Well, I've chosen to write these theorems in a way that has me say the fewest number of variables, which is why I wanted to give an actual number there. And it's also not the number that's in the paper. It's off by 1 because it simplified the statement slightly. So this is a So it's a level of distribution.
Is fixed, yeah.
Yes. So, or rather, the constant depends on a. So I mean, you want to know if it's arbitrarily high. Yeah. So the
Little a, I think.
oh, little a.
Little a is what I'm talking
Oh, little a.
That's the weakness of this. But it's still pretty good.
Wait, Simon, what do you mean by little a being?
Congruence to the residue class that you're summing up.
The level of distribution goes beyond what Riemann gives, but you have to fix the congruence class.
But we're not. We only. It's only for a single p. So if you're summing over different p, you could vary the congruence class.
Yeah.
So it's not. I mean,
You can't take a max. Right?
but this is. I mean,
So does the error term depend on little a or not?
no, I don't think so. No. Yeah, it does not depend on little a. Yeah. It depends only on f and big A. So this is exactly a gold standard level distribution, except
Yeah, sorry.
prime moduli only.
It's the analog of the divisor, 3 divisors.
Exactly. So the sort of history behind this is I think people were originally mainly interested in the level of distribution of the primes, or the von Mangelt function, so just putting the von Mangelt function in here instead. And studying that led to the study of the divisor function. There's many interesting results about that. And of course, a lot of these ideas were used in Yitang Zhang's breakthrough on bounded gaps between primes. But then the divisor function is the Fourier coefficients of a particular Eisenstein series. And so you might ask what happens for other automorphic forms. And so this is saying that for a special kind of Eisenstein series on GL3, we have a level of distribution that's beyond Riemann. And it should be possible to do this for more general Eisenstein series on GL3. If you just put different level in here, it would just require a little more work. Yeah, so the critical thinking here is how big this exponent can be. And it's greater than 1/2, which makes it beyond Riemann. Although, I mean, you may also kind of care about this problem of can you actually get to Riemann, because we haven't averaged over primes p, and so we can't use the Bombieri-Vinogradov method to get as good as Riemann. So there is a paper where we prove both these things. And the paper, most of the length of the paper, does not mention modular forms at all, does not mention like congruences and levels of distribution and L functions and any of these things. It is about algebraic geometry. And what I want to try and explain what I think is the most interesting aspect of this, which is how that transformation from these two concrete problems about modular forms into a problem about L-adic sheaves on varieties over finite fields occurs. And so,
Before we get to that, can I ask a question?
yes, of course. That's why I did this first, so that people could ask questions.
Is there a short interval version of this?
So if you were to try and do this thing over a short interval, you would not be able to use the Kloosterman sums wouldn't appear. This technique is going to tell you something about intervals, and you're going to get some kind of cancellation up to some kind of range, but you wouldn't be able to improve it using Kloosterman sums. I don't know off the top of my head what it is, but so you can figure out what it is based on the method.
Or presumably shorten it a little bit. I think he's thinking very short. And please say Kloosterman.
Say Kloosterman. I will, maybe not every single time, but I'll try. Yeah, so I'll show you shortly what the method is. You'll see that it can be adapted to say something about intervals which are somewhat short. There's also something I want to tell you about divisor sums in progressions. I'll tell you afterwards. Okay, so the new tool that we brought to both of these problems, they both depend on a single result, which is a result about bilinear forms. which I will now state, and then I'll explain a little bit about how it helps you with those two problems. So we're going to define, these are bilinear forms of Klosterman sums, which we're going to normalize. So these are it's completely nonsense. So put the parameter in. So these are sums over finite fields. And so I'll define them over finite fields instead of just mod p. So 1 over q to the k minus 1 over 2. We sum over tuples in this finite field that multiply to a of some additive character of the sum of the tuple. And so by a result of Deligne, this sum is bounded by a constant times q to the k minus 1 over 2. So this normalized sum is O of 1, which is nice because it makes it a little easier to figure out what estimates should look like. And the key bound is a bound when we're summing over two intervals, summing this Klosterman sum against two other functions, and these two other functions are totally arbitrary. So these are just any function from the natural numbers in this interval to the reals or complex numbers.
Perhaps the n is k.
Oh, yes, sorry. Yeah, this should be k. Yeah. So these are, oh, sorry, these are in finite fields. Oh, yes, so this should be p. Thank you, yes. Yeah, so specifically in the finite field fp. The bound is, I'll write it in a sort of silly way, which is I will hide everything interesting in the big O, and I'll explain why I'm doing that. So this is a bound in terms of the L2 norms of alpha and beta. And you can prove one bound in terms of the L2 norms just by knowing the bound on the Klosterman sums and doing Cauchy-Schwarz or whatever. So the trivial bound, we can take big O in the trivial bound to be root mn. And I don't want to write down exactly what the constant in the big O is here, because it's kind of annoying.
What does this notation mean? It's root mn. You don't want it to depend on m and n. You need to depend explicitly on m and n in this bilinear form. Is it like?
It's explicit. It's explicit. I don't want to write it down. So here's the statement, which is that if m is equal to n, if m is equal to n and greater than p to the 11 over 24, we get a power savings over the trivial bound. So that's the only thing that matters. I mean, I could write it's like.
I understand that, but don't you get something like m plus max? You know,
Oh yeah. Okay. Oh, it's m. It's okay. It's this. Okay. I hope you're happy. It's squared mn times m to the minus 1/2 plus m times n to the minus 3 over 16 q to the 11 over 64 with a q to the epsilon here, and then as long as m and n satisfy two inequalities. Yeah. So, I mean, it's something. But the important thing is that
But what is b now?
What is the b?
In your sum, in the left-hand side.
It's any function,
three coefficients.
arbitrary.
Oh, arbitrary.
Yes, and then anything with bound L2. This is alpha, and it's also arbitrary. Yeah.
That's also arbitrary.
Yeah. Okay. Yeah. So those are both arbitrary, and then so what's going to happen in these two problems is we're going to take our sum, we're going to apply a magical transformation, and Klosterman sums will appear, and we will fold everything that is not a Klosterman sum into either alpha or beta, and then estimate the L2 norm and apply this bound. So I'll explain. Well, yeah. So in this kind of bound, it's not very difficult at all to improve on this trivial constant as long as m and n are both greater than root p. And even if one of them is greater, you can do it with a way that's not too difficult. And so what's really important here is we can improve on the trivial bound by a power savings if m and n are a little bit less than the square root of p. And let me explain a little bit about how we turn this problem into a problem about cluster and sums. So you can write down in a pretty simple way we can write down the left side. We just expand this inner sum, and we get a sum that looks like this. We have the sum over n comma n. Their product is bounded, and their product is congruent to A mod q of lambda f of n. And though this condition that their product is less than x is a condition that changes very slowly as n and m vary. And so we can approximate this kind of condition pretty well using smooth functions. And in practice, we can break this up into different regions. We can express it as smooth functions that are separable into m and n. So we can write this sum, or we can reduce the problem of bounding this sum to bounding sums of the following form: lambda f of n, v of n, w of m, where these functions are smooth. And then we have a congruence condition. And so we're going to replace this congruence condition with an average over additive characters. So we're going to sum over u mod p of ep of minus a times u of the sum over n and m, lambda f of n, v of n, w of m, e of u and m. B. And here we have a sum of if we just look at just the sum in n, we have a sum of a function that's very smooth times an additive character times the coefficients of a modular form. If we were just summing a function that was very smooth times an additive character, the obvious and natural thing to do would be to apply the Poisson summation formula and see if it looks simpler on the other side. So this is not the constant function one, but luckily there is a version of the Poisson summation formula which applies when there's a modular form. So this is the Voronoi summation formula. And the Voronoi summation formula looks like this. If we sum over n our Fourier coefficients times a smooth function times an additive character, this is equal to the sum over n of our Fourier coefficients times a transform function times this is very important, but I wrote it down kind of small. So because we are on GL2 with trivial Nebentipus, this we should just maybe be the dual form, but it's actually the same because it's self-dual. This additive character is replaced with another additive character with a coefficient is inverted. And the smooth function is replaced with an integral transform of the smooth function. And again, I don't want to write down exactly what it is, because what's important is we can control this function by just doing real analysis and understanding integrals, which is much easier than either analytic number theory or algebraic geometry. But what I will say, like the Poisson summation formula, the longer and smoother this function is, the shorter and more concentrated its transform is. So we need this sum to be long enough, we need x to be large enough to make this sum on the other side controllable. And how do Kloosterman sums show up? Well, if you think about if you think about what happens if we do this, if you ignore everything that's not an additive character, we're going to get a sum that looks like this. The sum over u of EP of minus AU. And we transform this to the inverse. So we get plus u inverse m inverse. This is u in FP. And this sum, so this sum would appear in our sum, and there's also these lambda f of n, these other stuff would also appear. But if we just focus on this, we see that it's a Clusterman sum. It's a KL2 of minus a m inverse.
So in your theorem 2,
Yeah.
what's the k when you apply it? 2 or 3?
It's actually 3, because we're going to do a Poisson summation in the other variable, and this 2 will be upgraded to a 3. But I want to say, so this is basically how it appears, and it's a little bit more complicated than that. But we in fact do a Poisson on the other variable. We get another additive character in here. We collect them all, and we see there's a KL3. And then, there should be n here. Yeah, it's minus a and m inverse. Yeah, and this m inverse becomes an m when we do that, so it becomes a KL of a and m. And I guess I didn't put an a here, but you can put an a here. And yeah, so then basically everything else becomes either alpha or beta, depending on whether it depends on n or m. And we know how big our smooth function is. We know how big the Fourier coefficients of modular forms are on average, not individually unless they're holomorphic. And so we can put it in this form. And there's lots of different ranges of how big n and m can be, and we need to use different techniques in the different ranges. But in the most interesting range, the hardest range, we need to use this bound. And let me sketch what happens to the other one, although I will be even more sketchy, just because it would take too much time to go through it in detail. So what you have to do for this one is you write down your sort of naive guess of what the sum it should be. And the naive guess is, well, let's just pretend the L function converges. We sum over n and m of lambda f of n, lambda f of m, chi of n m inverse over square root of n times m. And then we sum that over chi. And this is not quite correct because it doesn't converge. But you can use the approximate functional equation, which requires putting a smooth function in here, and then a 2 magically appears because there's kind of both sides and it's a functional equation. I don't know.
The root number's 1.
Yeah, so the root number, yes, you first have to figure out what the root number is. And so sometimes it's 1 and sometimes it's minus 1. And so it depends only on chi of minus 1. So you may have to throw out half the chi's. And in some cases, you have to throw out all the chi's. And then the left side is in fact going to be 0. And you have to check the right side is also 0. But yeah, so you split into chi even and chi odd. And then you sum this over chi's, and you get so like if you sum this over chi even, you get the condition that n is congruent to plus or minus m mod p. But you can detect that again with additive characters. And you have a main term, and the main term is the sum when n is equal to m. And you can evaluate that by contour integration, and you get this main term. And the error term, you again have to break up into a bunch of different regions and use different techniques in the different regions. And one of the regions, you have to do this, again, because the Clusterman sums appear from these additive characters in Voronoi. Yeah, so when we're doing these problems of modular forms, because we're doing these very nice, long, smooth sums with additive characters, these additive characters get transmogrified into these Clusterman sums, and we just want to focus on them and just use our knowledge of Clusterman sums to enhance the bound to a better bound. Okay, so now I want to explain where does this bound come from, and how can we control this kind of sum. So roughly speaking, what we want to do here is we want to separate the the Klosterman sums and the alpha and beta, because we know everything there is to know about alpha and beta, which is not very much, which is their functions, and we know their L2 norm. And we know, maybe not everything there is to know, but we know a ton about Klosterman sums. But we don't know so much about how they interact. So if we want to bound this sum, we have to kind of separate them. And so the most naive way to do it, we try and apply some kind of like Holder inequality to bound some power of this and bound some power of this. And if you do that directly, you get the trivial bound. So what we instead do is we do some manipulations. We do 2 manipulations to which exploit the symmetry and the structure of this problem. And we then apply the Holder inequality. And the manipulations make it much more complex to estimate the norm on one of the sides. But we're able to do it. And by doing it, we get a little bit better than the trivial bound. So the first manipulation is we apply Cauchy-Schwarz to one of the variables. So I'll write down what that gets you. So we end up summing, let's apply Cauchy-Schwarz in the m variable. So we end up summing over n1 and n2, alpha of n1, alpha conjugate of n2. The sum. What part was not OK?
No, the 2 there, the reason there's root numbers 1 is because it's absolute squared in your first problem. So that's
oh, yes. Oh, good. OK. Yes, I mean, yeah, I do want to. Yeah, when we would expect if there was no absolute that it would be something small. Although maybe that's actually quite hard. Anyways, OK, so the thing is, we get a sum of KL2 of n1m, KL2 of n1m. OK. So KLKs. So if this inner sum were over an interval that was long enough, we could bound this inner sum directly by the Polya-Vinogradov method in a non-trivial way and get a non-trivial bound now. But m is going to be less than square root p, so it's not long enough. So we have to do this very strange method, which is the shift by AB trick, where we say, since this interval, if we shift this interval by a little bit, the sum won't really change. So we're going to replace this sum by the average over a certain set of shifts. And it becomes this very strange thing. Sum over A is in some interval, and sum over B is in some interval. You may not want to write this down depending on your personal preferences, but I'll let you decide. So we're again summing over n1, n2, alpha of n1, alpha of n2 bar.
I mean, you might point out that what you're really doing is you've got a matrix whose entry is K, L, K, M, N.
Yeah, so this thing. This
estimating the L2 norm of the matrix.
Correct. Yes, we're estimating the L2 operator norm of the matrix. And we're doing it by taking multiplying by the conjugate matrix. And then we do something which is sort of strange, but turns out to be a really good idea, which is we're just going to add, there's like a 1 over AB there in here somewhere. And we add times B to n1m plus AB, and then the n2m plus AB conjugate. And this allows us to do some kind of change of variables. And when we do this change of variables, the Holder inequality will magically become useful or more useful. So we define.
This is the trick that is often used for proving Burgess bound.
Yeah. So this is another way of proving Burgess is bound, or is another interpretation of the proof. It's really the same thing I think going on down there, and it I think turns out to be a little bit more elegant in this context. I was trying to see if you could adapt the proof of Burgess's bound to get a more conceptual proof of this, and I decided you can't. Anyways, so yeah, so we do this weird change of variables, and so which is that A times M is going to become R, and A inverse times N1 is going to become S1, and A inverse times N2 is going to become S2. And then this thing, what we sum is, we just take this, we just sum the Klosterman sums over B. We just focus on this inner sum over B. And this becomes Klosterman sum of S times R plus B. And this is S1. And this is S2 times R plus B. And then we have some other stuff out here. And now we apply the Holder inequality. So we raise this to the 4th absolute power, and we sum it. And we raise all the other stuff to the 4/3 power and sum it. And you bound the 4/3 power of that other stuff by elementary methods. And then we bound the 4th power of this stuff by very non-elementary methods. So I will state the result that is now entirely just a result about Klosterman sums that we proved that is needed to make this argument work. And I will state it as a lemma, because I think no one in the entire world would ever consider this statement except for its application to these bounds. So what we do is we're taking a 4th moment of a thing that's already a product of 2 Klosterman sums. It's going to end up being a sum of products of 8. And to arrange them, we define this horrible product of 4 sums, which is R, depends on some parameters, vector B, which is sum over R in FP. Actually, let me switch to FQ now, because this result is going to be true over FQ as well. KLK of S R plus B1, KLK of S R plus B2, KLK of S R plus B3, and you can't see the last part, but you could probably guess what it is. It's KLK of S R plus B4. And we have to put conjugates over these two. And then we do correlation sums of this function against itself in the, this is in the S variable. Oh, there's one more thing. So let me put it over here, which is we need an additive character.
So this is all part of the
Yes. So I'm now going to write down the complete sum that we bound. The complete sum in this notation is pretty simple. It's just the sum over R in FQ of this R of R lambda 1 B times R of R lambda 2 B conjugate is Q squared delta lambda 1 lambda 2 plus O of Q to the 3/2, O depending only on K. Okay, so what am I saying here? I want to view for each lambda, I just fix B universally, because the B aren't varying very much. We can fix them. For each lambda, this R is going to be a function of R. And I'm saying for different R, these functions are not correlated very much. And for individual R, they all have roughly the same L2 norm. And if you work out all the details of this, or more intelligently, you look in our paper to find all the details of this, maybe it's not that hard. If you do either of those things, you'll see that this is precisely what we need. And this is for the B vector has to be not in delta, which is some algebraic subset of bounded degree. So let me say, if these things we said were O of 1, so under square root cancellation, this R thing would be of size about O of root Q. And so we're saying that we do get some kind of square root cancellation on average as part of this statement. And then when we sum them against each other, we get a further square root cancellation. So now I only have to explain to you how one might ever prove something like this. This is a complete exponential sum. And I'm going to talk to you about the general theory of how it is that we prove complete exponential sum bounds. We'll give you.
Before you erase it, what is the main term? Is it x log x or is it x? Yeah,
In this sum,
Yeah.
that is just, it's just x over p.
So it's x log.
Oh no, it's log x. Log it. So if lambda f were not a cusp form, were a divisor function, there would be a power of log. I don't know off the top of my head.
You have to worry about the b.
Oh, you're saying like this.
That's like the circle problem amount of cancellation. That's like, yeah, that's a.
So I'm worrying that it's smaller than the remainder.
Oh, it might be, yeah. Yeah, so maybe it's just a cancellate. Maybe in some cases I don't need to have the main term in here. I mean,
Okay.
it's just a bound. It's just bound on this sum.
So if f is a cusp form, then the error term swallows up.
Yeah, I think so. But yes, it's still a non-trivial result despite that fact. Yes, this is a good point. I think we just wrote it like this, so it would look more like other level distribution results that are more popular. Okay, so let me give the incredibly quick introduction to if you have a sum, a complete sum over all of fp of some function. Let me actually write this over to one side. How you prove that it's bounded. Or how you prove a good bound on it. It's not so hard to see that the sum is bounded. So the idea is you have to relate it to what is called a trace function of a sheaf. Trace of Frobenius acting on a sheaf at x. And let me give you the shortest. These should be FQs because we can just work over finite fields.
Capital F. What's capital?
Okay. So sorry, this should be a curly.
Yeah, that's capital.
This is a function.
Any function.
So some functions. So let me say. So what is a sheaf, and which functions can we represent as trace functions of sheaf? Let me explain that very quickly. So x of variety. Took a very rapid turn in the contents of this talk. A sheaf on x for me, or a least sheaf on x, is a L-adic representation of the top fundamental group of x. A sheaf is a least sheaf on a dense open subset plus some singularities. So if you believe me, I have a notion of the fundamental group, then you understand this definition. And I'm saying there's a suitable way of extending it with singularities that gives you a nice theory. In this case, this fundamental group is sort of like a Galois group. So just as there are Frobenius conjugacy classes in Galois groups, there are Frobenius conjugacy associated to primes. There are Frobenius conjugacy classes in here associated to points. Frob q at x associated to in pi 1 of x. And so we just take the trace of this conjugacy class on the representation. And again, there's a suitable way of extending it to singularities. Now, what functions can we actually write in this way? There are two basic kind of functions we can write on this way, which is, OK, let me just write over here. If f of x is the multiplicative character of some rational function of x, this is OK, where we can construct this representation using Kummer theory. If f of x is an additive character of a rational function of x, this is OK, and we can construct it using Artin Schreier theory. And the last and most important way of constructing these things is that if f of x is a sum of some other function, and it's a complete sum over a finite field, then if g is good, that implies that f is good. OK, and these three tools are precisely what we need to write all the functions we care about in this way, because we know the additive characters are fine. So by summing them, we know that the Clusterman sums are fine. Multiplying them together is fine, although I didn't write that down. And we have to sum them again.
F is some low degree expression.
So you have to keep this.
If you start multiplying, make the algebra, you have to control the complexity.
Exactly. So yeah, there's some kind of notion if you want to do a limit, you have to be. But so this is, by construction, we want to establish this identity. And then we will apply, we got a very long equal sign. We apply the Lefschetz formula.
So you actually have the function.
Yeah, so
How would you define?
I explained how to do it in 3 cases.
Okay, so maybe.
Everything else is left as an exercise.
Your x you defined over FQ?
Yeah, so these are varieties over a finite field. And I could talk also about varieties over other bases and varying the finite fields. But I don't have very much. I'm trying to keep things as simple as I can. But But there are ways of doing this as varying the finite field and make that good. We want to bound this sum. And I am an algebraist. I don't really know how to bound things. I know how to prove identities. So the way we're going to bound it is we're going to prove an identity. And we're going to hopefully use that. So
the trees why is there some x in this trees?
So the x is down here. So it's the Frobenius element at the point x. And I wrote it up here because of how singularities of sheaves look. It makes more sense.
But this x should be a point on the right x.
Yeah. So this is for. Because I said it is. Yes.
But your sum is over sum over x.
Just over for FQ, just over the finite field. Oh, so in this case, the variety is A1. I'm just saying for simplicity, the variety is a line. So the points are FQ. And I mean, all the sums I'm considering are sums over lines. So, I mean, yes, there's a more general. But so what can we say we can use about this sum using algebraic geometry? We can use the Lefschetz fixed point formula. And the sum looks like this. I'm going to write all the terms out. It's the trace of Frobenius on the first compactly supported cohomology group of the sheaf minus the trace of Frobenius on the zeroth on the first one plus the trace on the second one. And then we have to stop because of a cohomology vanishing result. And if we want to know how big these sums are, we use a theorem of Deligne. We use the Riemann hypothesis, which says, so if if this function is O of 1, then we can depending on how we constructed the sheaf, we can probably also prove that f is what's called mixed of weight less than or equal to 0. Which is the technical condition I need to say that this sum is O of 1, this sum is O of root q, and this sum is O of q.
I just want to capital F was something in the algebra of some other functions. The guide which you make the key identity is some specific kind of a.
Yeah. So I'm trying to say that this is a strategy.
Okay.
So step 1 of the strategy is to write it as the trace function, and so.
F is a little too arbitrary in the way
Yeah. So, I mean, you can really ignore this thing and just say.
You're doing it for characters, for those sums, and then whatever you have your basic functions, you're building other functions out of that. Nothing further there. Right?
Yeah, nothing. Yeah, at least not on this paper. So, yeah, that's what we're doing. Yeah, it's precisely those functions and a bounded complexity, and using that. So the big O in here, it really depends on the dimension of these groups. Because what Deligne really proved is he proved that the eigenvalues were at most q, at most root q, at most 1. So the constant in these big O's is just the dimension of the groups. So you can see immediately two things. You can see because this is O of 1, there's a trivial bound that's O of q on this sum. And so if I cannot control, if I can't say something about H2, then I will not be able to give any kind of non-trivial bound in this sum. But you can also see if I can control H2 pretty well. For instance, if I can show that it vanishes, I immediately get a very strong bound in this sum. I get a square root cancellation, which in most cases is the best bound you could possibly hope for. And it's even with a constant and not q to the 1/2 plus epsilon, which is nice in some circumstances, although it's rarely essential. And then I don't always need to prove that this is vanishing. So here I want to prove the sum is equal to some other thing plus an error term. And what I'm going to try and show is that this other thing comes from this, and nothing else is up here. So I have reduced my problem of analysis of bounding the sum to some kind of problem of topology. I have fundamental groups here. I have some kind of cohomology theory. And I haven't told you which fundamental group or which cohomology theory it is. But you can trust me that they actually exist and that we can use a lot of techniques that are borrowed from the original usual topology to study them. Let me say the most basic fact about how you control H2. So if you want to control H2, you can do the following argument. You can take, I said there's an open subset on which it is least, so take U on which f is least. Then we can relate the cohomology of the whole space and f to the cohomology of U and f by excision. And because this is a nice least sheaf on a nice smooth thing, I can do a Poincare duality. So this will be the first cohomology of the dual sheaf dual. So this is Poincare. And as usual in cohomology, H0 is not so hard. So this is a representation of pi1. And this H0 is just the invariance of pi1. So this is the pi1 invariance of f dual. So you see, to bound this sum, I have to know something about this representation of pi1. In this case, I have to know the co-invariance. Here, because I'm actually tensoring 2, if you work out what this means, it means that I have to show that these representations of pi1 of the R line, these representations are irreducible, and that they are distinct for different lambdas. And it's usually not so hard to show things are distinct. You just have to find any invariant that distinguishes them. So the hard part will be to show that they're irreducible. And there are many tools to show irreducibility of sheaves. If there's not much summing going on, it's just additive characters and multiplicative characters, it's pretty easy. The sheaves are constructed directly, and you can just directly see what this representation is. But if there is summing, then your sheaves are constructed through cohomology. And to understand what these pi1 representations are, you have to understand how pi1 acts on its cohomology of a family of varieties. So the idea of Lefschetz that's helpful here is if you have some family of varieties with some singular points. So each point of the space has a fiber that's some variety, and most of them are nice and smooth, but some are singular. Then if you want to understand how pi1 acts, that's pretty hard. But what you can do is understand how pi1 acts if you take a loop in the fundamental group. It's a very small loop around the singularity. And what's going on is that there's a reason there's a singular. There's only a singularity in the cohomology if there's a singularity in the actual families. And you can figure out something about the cohomology in a little neighborhood of the singularity in the base just using a little neighborhood of the singularity in the fiber. And what this enables you to do is you can study the cohomology locally by studying the varieties locally. And the equations defining them become much simpler. So if you imagine this singular torus I created, sort of is hard to see. If you zoom in, it's like a much simpler thing. It's just two things glued together. So Grothendieck and Deligne figured out how to do this stuff in characteristic P. They figured out how to do this stuff in sheaves. So what you have to do to understand the local behavior of our sheaves is to understand these R sheaves, is to understand locally what these products of Clusterman sheaves look like. And a lot of local computations of Clusterman sheaves were done by cats. We understand that pretty well. And you have to sort of work very laboriously at each of the different points to make sure the local monodromy is what you expect it to be. And when you do, you can get the result. So can I say one more thing? Do we start a little late, or did we? All right. So I'll say one more. I'll say one more thing, which is we didn't prove the irreducibility of these representations directly, because we don't know how to do that. The local information that we can get is not enough. We proved the irreducibility using families. So there are all these extra parameters that we have in this sum. We have this lambda parameters, and we have the b parameters. And basically, you can see if you sum, if we take this correlation sum, r of r lambda b, we're just going to take the self correlation, so the square sum. If we sum this over an extra parameter, like we sum over lambda, then the sum will simplify. You can cancel the terms, and it becomes much easier to prove this estimate. And what that means, we can actually reverse this and go back and say, well, this is irreducible. It tells us something about the sheaves. It tells us we have this family of sheaves, which is a sheaf on a larger space. And that sheaf is itself irreducible. And then from there, using some local information, we can go and say that the general fiber of this family is irreducible. So you have a sheaf on some it's really the complex line minus some points, which are actually the minus BAIs, cross the affine line. You have a representation of the fundamental group of this, and you restrict it to one of these lines. You know it's irreducible for the generic one. If we were in characteristic 0, we would be done immediately, because the fundamental group of this product is just the fundamental group of this thing. And so if we know it's irreducible on one fiber, it's the same on every fiber. So it's irreducible on every fiber. If not true in characteristic P, using our entire theory, you can construct counterexamples. But a result of Deligne's semi-continuity theorem tells you how to tell when the cohomology of the sheaf is the same for each fiber. And then using the cohomology of the sheaf tensor as a dual, we can give a criterion for the irreducibility to be the same on each fiber. And we check that condition by checking a local condition at each of the points, which we do using this vanishing cycle. And that's really how the irreducibility proof goes. That's all I have to say.